everyone, in this video, I will introduce you the spiking capsnet. Convolutional neural networks (CNNs) have obtained tremendous success in various domains, such as object classification, visual tracking, object segmentation, and so on, due to the powerful feature representation ability. However, there still exist several limitations associated with CNNs. First, high-level features are obtained by low-level weighting features while ignoring their spatial relationship. A face is just a simple combination of the eyes, nose, and mouth features. Even if the position of these features change relatively, the classifier will still consider it a face. Secondly, the commonly used pooling operation throws away precious position information of the object and is destructive to the spatial relationship. To tackle the problems, CapsNet utilizes a group of neurons to donate more properties, which are called capsules. These properties represent the attributes of the corresponding feature, such as position, color, and texture. The length of the vector represents the probability of these properties. In addition to the capsule concept, the routine mechanism is used to ensure the output of the lower capsule to the closely related higher capsule. Although CapsNet mimics the multi-layer visual system with a sparse tree-like structure, it is still far from the human brain's information processing mechanism, considered as the third-generation artificial neural network. Spiking neural networks use discrete spikes to transfer information, which is more biologically plausible and more energy efficient. We introduce the capsule structure in the spiking neural network so as to take full advantage of the spatial and temporal characteristics. There are two main differences between the capsule neural network and the convolutional neural network, as shown in the figure. First, the capsule neural network uses a vector to represent the internal properties of an entity. Second, the capsule neural network uses a routine mechanism to replace the pooling layer in the convolutional neural network. The low-level capsule output is used as the input of the corresponding high-level capsule to represent the relationship between the part and the whole to achieve translational equivalence. The original dynamic routine uses the inner product to measure the consistency of neural activity before and after the synapse. When extended to SNNs, the information in the network is represented in a vector of binary spikes. Compared with the real-valued artificial neuron, in addition to the part and the whole relationship between the low-level capsule and the high-level capsule in the spatial domain, there is also the spike timing information to describe the causal relationship between spike trends in the temporal domain. Suppose only the original dynamic routine is extended to SNNs. In that case, it equals to Herbert learning, only considering the activity of neurons before and after synapses, ignoring the relative order of spikes firing between them and missing the temporal information. Moreover, since the SNN uses discrete spikes to transmit information, the sparse spiking fire activity will make the weight of the network not updated for a long time. Therefore, we consider extending the Herb-like learning to the STTP learning rule, which we call STTP routine, to strengthen the connections between the low-level and the high-level capsules in spatial and temporal domains. Our spiking CapsNet combines the advantage of SN and CapsNet and shows strong robustness to noise and affine transformations. By adding different noise to the test dataset, experimental results show that our algorithm is more noise resistant than other methods. Similarly, our spiking CapsNet shows strong generalization to affine transformations on the affinist dataset. As shown in the figure, when the MNIST whereas fashion MNIST datasets are added with noise, the classification performance of other algorithms degrades rapidly when the noise is high until the classification ability is completely lost. However, our spiking capsnet algorithm shows strong noise robustness in the face of noise on both datasets. We also tested the generalization of spiking capsnet for affine transformation by training spiking capsnet on the MNIST training set and testing it on the affine test set. Affine is an extended MNIST dataset where each sample is an affine transformation of the corresponding sample in the MNIST dataset. The size of the samples is 40 multiplied 40, as shown in the figure. Our model is compared with the spiking convolutional neural network, the traditional convolutional neural network, and CapsNet. In addition to compare the robustness to affine transformation more fairly, we follow the same early stop operation. We stop training the model when the training accuracy achieves 97, 98, and 99%, and test it on the affine test dataset respectively. As shown in the figure, our spiking CapsNet achieves a higher performance compared with the spiking convolutional neural network and the convolutional neural network. We have uh, implemented the corresponding code in the BrainCog, and feel free to contact us if you have any questions. That's all. Thank you.